So conditional probability. That's great. Conditional probability. So you have noticed that much information, every sort of bit of information can be very important for the problem at hand. Right? So you have to keep track of the sample space when you're solving those problems. Now, the sample space, the true sample space, is actually enormously vast. Think about it. Even if you throw a coin, you actually have, as you're throwing the coin, you have people walking up and down the street. You have birds flying in the sky. Grass is slowly breaking from the ground. All right, so what part here is important? Do we need to, when we throw dice, do we have to worry about galaxies spinning away from one another? Or we can ignore that fact. The sample space that you're talking about is always, when you think about what's happening, it's always the universe at large. And today's lecture, I will show you that that's indeed the case, I hope, okay? And then we will talk about it once we get there. So before we understand, why is it that our sample space, for example, when we just throw a coin, why do we usually think of the sample space as just coin being heads or coin being tails, a very primitive universe? For that, we need to understand how probability is updated based on some particular circumstance that happened. Okay, so that's what you call conditional probability. Something is happening. So for example, you throw a coin and it happens to be that the table on which you throw the coin is brown. It's brown wood of sorts, right? Or red wood, I don't know, right? That is conditional probability, that something else is visible besides the coin. So we denote it by this notation, right? So if we have a sample space S, and a particular event F from that sample space has happened, what's the probability that the event E happens given this information? Okay, so that's called the probability of E on the condition that F happened. Okay, and here is a very, very basic experimental verification of something here, right? So I'm sorry if my English breaks, it's because, I don't sleep. It's in all languages. I lose my ability to speak grammatically. It begins to fall apart. So 2 coins are flipped 20 times. Let E be the event that coin 1 comes up heads. And let F be the event that at least 1 coin lands up tails. So these were the outcomes, right? So I just simulated it and those were the actual outcomes of throwing the coins, okay? So you see, we are interested in the probability or estimating the probability based on that information of E happening given that F happened. You understand? So we are asking this problem. Suppose that it was observed that one of the outcomes was a tail, right? F means that 1 coin is a tail. What's the probability that coin number 1, first coin, is heads? Good. So if I were to conduct this experiment, then what do I observe? I observe here. I put in blue. I put the event F, right? So if I see the outcome tail, that means one of the outcomes was a tail. So that's part of event F. If I see here tail head, one of the outcomes was a tail, so that's part of my event F. Yes. So what I'm trying to understand is if I restrict to the frequency, if I construct a table, you remember that what you have is a non-deterministic sequence. Yeah. So each new term in the sequence is new. But now I delete from my sequence everything that's irrelevant to F. Only F has happened, okay? And we want to know the relative frequency of the event E inside of F. So you see, here you can see everything that is in a red box, that's the event E. Yeah, so the first coin is heads, first coin is heads, first coin is heads. But if I am interested in the frequency of E within F, I delete everything that's not F. So everything that doesn't have a blue rectangle is deleted, right? And some of the terms that are deleted are actually outcomes in E that do not match with outcomes in F. So far makes sense, guys? Right? I'm hoping that I'm not losing you, especially this very critical instance. And then we observed here that in this experiment, the number of occurrences of E, it's 13 in general. So so there are 13 red boxes. And the number of occurrences of F, actually 14 occurrences of F. Yes? So if I want to measure the occurrence of E within F, I delete everything that's not F. And then what is remaining, what occurrences of E are remaining, it's the intersection of E and F. It's where you see blue and red squares. You understand? You understand what we're trying to do? We're playing this experiment and we want to know if F happens, how frequently does E happen? Right? So that means that when we run the simulation, when we run the unrestricted simulation, we ignore all outcomes that do not correspond to an occurrence of F. Right, so that means that our table only contains the blue squares. Let's say if it were in order, so it goes like this. So I delete the reds, and it will be first, second, third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12, 13, 14. You understand? I should have maybe numbered them, but you understand what I mean, right? So this is my column that I measure the sequence for. And within that column, I underline how many occurrences of F I had, because that's the only possibility that E happens. It must be part of F. And there were 7 such occurrences. Good? So in other words, you see, so F has become my new sample space. My new sample space because I don't allow any outcome other than F. Artificially, perhaps, but that's my set of universes. Only F is now my universe, not the original space. Right? Because I delete inevitably any outcome that doesn't correspond to F. So my universe is F. So then I can do the same procedure. I can carry out the measurement as I did before. And I think, well, nature will show me if I provide enough trials, if I provide enough instances of F, and I count how many of those instances were instances of E, I will know the preference of E within F, within that sample space. How frequently does nature prefer this outcome E to occur? Guys, before I continue to say anything more, is it clear?
Yeah, it's clear so far.
What I said so far clear. My inability to speak well today, maybe never I speak well, but today especially, it's not affecting you too much. Yes, I hope so, because I really want to explain it, right? I mean, I was yesterday like, oh my God, what an amazing idea, right? And then I fall asleep, wake up, everything is unimportant. Yeah, that's how it happens. So this is what I then mean, right? So the probability of E given F is just the number of occurrences, roughly the number of occurrences of F in the denominator, and then in the numerator, I have the number of occurrences of E intersect F. Why do I intersect with F? Because again, E unrestricted could have occurrences that are outside of F. But if F is my sample space, I exclude those occurrences, right? As I did over here, just boxes that have a purely red outline, they are excluded. So far, so good. You understand what this formula, where I come up with this formula. So, of course, the number of instances of F is very small, just 14. You saw with throwing a coin, you need quite many of them. You see, we were seeing good convergence once we were reaching into the thousands, right? So this is, of course, not a good number, and therefore this estimate of probability isn't a good estimate. It's just to give you the idea. You probably want to throw it thousands of times. You want the domain F to be maybe 1,000 or something, right? To give you a better set. Because the idea is you have to have many experiments, many outcomes of the sample space. You test them. So, but based on this procedure, we estimate, so far, our estimate is that the probability of first coin being heads, given that at least one of the coins is tail, to be 1/2. And that number might not be right at all. Maybe it will change if we conduct more experiments. Yes? What we truly want to do is this. Just as with probability, we want to run the number of outcomes of F must go to infinity. Yes. In other words, if F is my sample space, I want to give nature many attempts, many trials to restore justice, to show how preferable is the outcome E within F. So I push a limit as n of F goes to infinity. So that's just the definition of probability, where this is just how many instances of F have occurred. Yes, the frequentist definition, where that's my new sample space. Right? So then I switch, look at it. I switch from this limit, I switch to the limit as n goes to infinity. And the reason I switch it is because I presume in most circumstances that the outcome F does not have a zero chance of happening, right? And it means what? If it does not have a zero chance of happening, means that if I run my experiment, my unrestricted experiment many times, I will also have many instances of F. So just like over here, if I have millions of unrestricted experiments, I will have quite a lot, at least 1,000 maybe, or some sort of number of blue boxes. It will increase. Because why? Because the probability of F is not zero. It must somehow be keeping up with the denominator, right? So if n is large, the number of F must be large enough to not be crushed to zero, right? So that implies that it will also go to infinity as a function of n. I can switch. But if I switch to n, I can now divide the fraction top and bottom by n, and push the limit. Now, by hypothesis, the numerator limit, it's just the probability of EF, remember from chapter 2, and the denominator limit is just the probability of F. So we arrive at this interpretation. The probability of E given F in this restricted sample space is just the probability of EF divided by probability F. Before I move on, guys, very important idea. In most books, they just kind of throw it at you. They say, well, that's the definition. I try to explain why that will be the definition, right? Why do you make it a definition? I understand it in terms of the frequentist point of view. Push the limit, you have this formula coming around. Does it make sense? If you have any comments, guys, write it, because it gets complicated, right? As if chapter 2 was a little complicated, this chapter is worse, right? So we need to understand that. And here I just again explained it. Now, here is a particular problem. Let's see if you can actually solve it without my help. Two fair dice are rolled. What's the probability that first die lands on a 3, given that the sum of the dice is 8? Do you understand the question? So if I roll 2 dice, unrestricted, there are 36 possibilities for the outcomes. But here it was observed that the sum on them is 8. That's my F here. Hopefully not your F. Go ahead. Okay, Valeria, interesting. Thank you. And let's see what the rest of you will say. Paula, thank you. Thank you, Naomi. You seem to have a consensus. What about the rest of you? Okay. I'm waiting, guys. I'm not pressuring, right? Wonderful, Shabeli, interesting. Alejandro, a lot of agreement here. Okay, Kazi, thank you. A little bit longer, guys, and then let's move on. All right. How about we look through it? Yes, let's solve it together. So the original sample space, again, there is still this question that might bother you at the back of your head is why is this the original sample space? When you throw a pair of dice, it's not happening in a vacuum, right? There are other things involved. So, but let's for now ignore the difficulty and say the Kafka document is as we used to have it, die one outcome, die two outcome, right? That will capture all the possible universes. There are 36 universes in total, but we may pick the sample space F that contains the outcomes 2, 6, 3, 5, and onwards, because those outcomes are, well, it's what happened. We have a sum equal to 8. So it's one of those 5 outcomes, right? There are 5 outcomes over here. You see that? And only one of those outcomes corresponds to the probability, well, so only one of the outcomes corresponds to the event that the first die is a 3. Only one, yes? Now, an important thing to notice is that we're assuming, right, that there is no preference among outcomes in F, correct? We will actually later justify why this is a correct assumption, but you see, it doesn't feel that nature will prefer. If F happened, it doesn't seem that any of the outcomes in F are favorites. They're all equally favored, which means the probability 2, 6 happens is 1/5, this happens 1/5, and onward. So the answer is indeed 1/5. Okay, that's doing it with restricted sample space. Okay, we can just to illustrate that formula. I would have, of course, not bothered with it for this problem. I would have just right away see that's my restricted sample space, only one outcome, 1 out of 5, and everybody who answered it are absolutely correct. But just to humor me for a moment, let's see what this formula will do. So where we calculate the unrestricted sample space, right? So to calculate probability of E given F, it's the same according to the formula we derived as to calculate the probability of the intersection of E and F divided by the probability of F. Yes? So intersection of E and F, that means first die is showing a 3 and the sum is 8. So that means only this one outcome. That's the intersection. It's the probability of one outcome. Yes? And what is the probability of F? It's the number of outcomes in F divided by a total number of outcomes in the sample space. So that is 5/36. But the probability of 3,5 is 1/36. So I can multiply top and bottom by 36. I also obtain 1/5. Yes? Here is the next question. A fair coin is flipped twice. What is the conditional probability that both flips land on heads given in part A? So answer A, or you can write A, and then the answer B, and then the answer A. First flip lands on heads, and B, at least one flip lands on heads. You understand what the question is? So let's solve A and then B. First toss of flip of the coin is heads, and here in B, at least one of them. And I am asking what's the probability that both of them are heads, given this information. Okay, Valeria, thank you. Thank you, Naomi. Thank you, Chabeli. Thank you, Abhishek. Great. I'll wait a little longer and then we will reveal the answer. Yes? Thank you, Said. Great. I'm very nice. It's very nice. I'm happy with what I'm looking at. And you, Melissa, how are you doing? Are you there? Great. I'm dying to hear what you think of this problem. And ask me, guys, if anything is unclear about the idea, ask me, right? Thank you, Kazi. All right, let's look through the solution. So B is the event both flips land on heads. And let's in A have capital A be the event that first flip lands on heads. That means we have only two possibilities, heads, heads, or heads, tail, correct? And the probability of B given A, there is no preference between, if we know that A happened, first flip is heads, so we know that either this outcome happened or this outcome happened, and there is no preference between the two outcomes. And I think all or most of you answered correctly. The answer is 1/2, because you understand why, guys, right? I work with a restricted sample space. this outcome and that outcome are equally likely. Good. I don't need to work with the unrestricted sample space. Now, what's the difference in B? So what I said, event at least one flip lands on heads. At least one flip, that means I have two possibilities, either head-head or head-tail or tail-head. So there must be at least one heads. Good. So I am only deleting, I'm excluding only one outcome. And again, there is no preference. Nature does not have a preference between any of the three outcomes. And the answer is 1/3. Good. And let's just make this observation concrete. How do I know there is no preference between them? So we make this observation. If S is a sample space with equally likely outcomes, then so is the restriction to any subset F. If I make that my new sample space, it will be a sample space having equally likely outcomes. Good. So let's suppose that it's a finite sample space. It has only n elements, and F has fewer elements, possibly, maybe not n. Are there n or less? So if X is some particular outcome in F, I want to show that probability of X given F is going to be the same regardless of what I pick. So it's going to be 1/m. That's my goal, to show it, right? So because if F has m events, m outcomes, then the probability of X should be 1/m, if that's correct. So what's the probability of X given F? It's the probability of X intersect F divided by probability F. Probability of X intersect F is just X, because F contains it, right? So it's just probability of X divided by probability F. But we are dealing with a sample space S that has equally likely outcomes. So the probability of X within S is 1/n. And the probability of F within S is m divided by n. Remember that we spent such a long time discussing those sample spaces. Multiplying everything by n, I get 1/m. Everybody understands what I just justified? It was, I think, somewhat obvious. If we have the mother space has equally likely outcomes, then if any subset happens, then any outcome in that sample space, in that sub-sample space, has equally likely outcomes. Yes? So that's what we did over here. We had the coin was fair. We threw it 2 times. The original sample space had 4 outcomes, and the probability of each particular outcome was 1 divided by 4. But now 1 is deleted, so we only have 3 outcomes. It will be now 1 divided by 3, and based on this argument. Good? Here is another question, possibly slightly harder, okay? And possibly it hits closer to heart. Student is taking a 1-hour exam. The probability the student is finished with exam in less than X hours is X divided by 2 for all X between 0 and 1. So for example, the probability the student finishes the exam by the end of the hour is 1/2. So it's not likely the student is going to survive. Given that the student is still working after 0.75 hours, what is the probability that the full hour is needed? In other words, the student doesn't leave until the exam is taken away from him. Interesting. Thank you, Kazi. But why not sure? Well, all of them are confusing. It will be worse, trust me. I hope what I worked below will be confusing you tremendously. Almost one. Depends what's almost. Almost is subjective. My exam is going to be worse. This is a very silly question, right? I thought which question to ask. I think this one is not hard enough. That's why it's not ready. I only wrote 5 of your problems. The rest I want to think this is I don't like it. I want to make a harder one for your joy. Last semester they said it wasn't hard enough, so I am trying to improve. I don't cry. It's gonna be okay. No worries. No worries about this class. Everyone's going to get 100, which means the 100 is not going to be worth too much. Abhishek, okay, thank you, Abhishek. Abhishek says 0.25. Appreciate it. So be careful. Okay, remember what I'm asking, guys. I'm asking the probability that the person will require full hour. Okay, not that the person will be finished necessarily, right? But that it requires the full hour. In other words, let's say, please let me finish, and then the exam is taken away. Okay, that's what you should imagine. Another 3 minutes, guys, and I will reveal my solution, yes? Alejandro says 0.9, Shotaro 0.875. Oh, Alejandro says, sorry, 0.8. Thank you, Alejandro. All right. All right, 1 more minute, guys, and we talk about it, yeah? Or yes, x bigger than 1, yes, Chabeli, that's right. It can be confusing in notation, but your logic is very good, I think. Okay, we will go over that, don't worry. Wonderful, Chabeli. I'm very happy to hear that. Thank you. All right, guys, let's talk about this problem. Don't worry about it too much. It's a rather stupid problem, right? Just to illustrate symbolic ideas here, right? So here is, so it's nice to have some logical symbols here. So let f sub x be the event that student is finished in less than x hours, okay? So because why do I say like this? Because, well, we know that probability is x over 2. The probability that f sub x happens is x over 2. Good. So what is it that we're interested in? We're interested in the probability that student is not finished before 1 hour. Yeah, then if it takes the full hour, means that the full hour was insufficient. So he is not finished in that 1 hour, given that he is not finished in 0.75 of the hour. And for this problem, perhaps it's nicer to use this unrestricted probability. So what is this? This is the probability of F1 complement intersect F0.75 complement. Again, guys, this is confusing. It confuses me easily as well. What this means is that the student is not. You see, the complement means not finished below this hour mark, and this means not finished below the 1 hour mark, right? And clearly, if he is not finished below the 1 hour mark, that implies he was not finished before the 0.75 mark. So the intersection is just F1 complement, which is what Chabeli just asked. Yes. So this is the crucial step, the intersection. If you got through it, you solve the problem. Now, how do I solve this quotient? Well, the probability of the complement is 1 minus the probability without the complement. Right, so we have 1 minus probability f sub 1 divided by 1 minus probability f 0.75. What is the numerator? Probability finished before 1/2. Sorry, before 1 is 1/2. Do you agree? Probability the student is finished within the hour is 1/2. based on the information over there. And the probability the student is finished within 0.75, it's 3/8. 75 is 3/4, divided by 2, it's 3/8. So I then multiply everything by 8, numerator and denominator. I have 4 on the denominator, 8 minus 3, so it's 4/5 or 0.8. So thank you, Alejandro, thank you, Chabeli, and thank you for everybody else who got this answer. Beautiful. And I think Kazi did as well, right? I hope I haven't forgotten anybody. But if you haven't gotten it, it can be confusing. You just symbols can sometimes confuse you. Good. Everybody understood how I solved this? All right. And now let's talk about slightly more interesting problems, right? I hope you would find them funny. Okay, so first one of them, again, I talked to one person, so I thought of this problem. Maybe I heard it some time ago, or something similar, I'm sure I've heard, right? The crown prince is always the eldest male offspring in the royal family. If the crown prince is one of 3 siblings, what is the probability that he is the oldest child? Question makes sense? I hope you are reading your Kafka before going to sleep, guys. Yes, it helps. Kazi, thank you. Thank you, Kazi. You always add maybe or perhaps, or you have to trust in yourself, right? Abhishek, thank you. And yeah, I don't know, scary, what do you care? Do I look scary? I cannot bite you. I'm behind this glass in this aquarium. What can I truly do? Okay, Abhishek, thank you. Essentially, Abhishek, I think you are trying to say 1/3, right? 0.33, I mean 1/3. Four over 6. Thank you, Naomi. So in a minute, I will reveal the answer since we have what? Not too much, right? Not too long to, I want to finish this lecture today, possibly. Okay, guys, you ready? We can stay, of course, longer. If you're willing to stay with me extra 30 minutes, great. Right? We can stay longer. I liked when you think about it. But I want to finish it today. Okay, guys, are you ready? Let's look at this problem. So it's easy to solve it if you are thinking like a bureaucrat. Okay, what does it mean that what is a crown prince? He is the oldest male here. Here I see, because I love bunnies, as some of you know. All right, so that's why I confuse air and here. But here is my reduced sample space, right? I have the bureaucratic document in which I have 3 boxes for the gender of oldest, middle, and youngest child. So what are we observing, right? Well, the crown prince might have been the firstborn boy, yes? In which case, if that's the situation, there are 2 possibilities for each of the remaining 2 children, right? For each of them separately. So this has 4 possibilities of being filled out. This is exclusive, right? So maybe the first child was a girl, and that means that the middle child perhaps was then a boy, right? So now he is the oldest boy, he is my crown prince. So there are only 2 possibilities of that. You see, those are disjoint. And finally, which some of you might have forgotten, if both children here are girls, the fact that I have a crown prince means I have a boy, right? So how many possibilities? It's 4 plus 2 plus 1. 7 possibilities in the sample space. Now, being born, whenever 3 children are being born, there is no preference, supposedly, right? I mean, we're assuming it's like throwing the coin. There is no preference which child was born when. Do you agree? So in other words, there's no preference for all the possibilities. Could be all boys, all girls, boy, girl, any of the 8 possibilities. Yes. So here we have 7 equal possibilities. Do you agree, guys? 7 equal possibilities. Kazi was absolutely right, and 4 of those possibilities correspond to the king or the crown prince being the oldest child. So the answer, as Kazi suggested, he was just unsure, but I'm very proud of you, Kazi, is 4/7. The answer is 4/7, and this is how I reason it out. You understand? I made many mistakes until I decided I will be a bureaucrat. And when you're a bureaucrat, you don't make mistakes because it's documented. Good. Are we ready for the next problem? Yes. You understood how I calculated it, yes, guys? So 4/7 is my probability. Now, keep your guard here, especially from me. So you have young Dolores sees a strange man, her mother's new tenant, looking at her through the living room window. Each of his first and last names is either Humbert or Quilty. She knows one of them is Humbert. What is the probability his full name is Humbert? Humbert? If she is wearing one of 3 pairs of her favorite sunglasses, pair number 1. You understand my question? Do you know what it is about, guys?
No.
Not really, no.
You're not reading too much. Not good. That's why I love those moments. I see that I'm laughing to myself. Oh, I'm so clever. Humbert. No, it's not Wizard of Oz. So you say you don't know which person you're dealing with here, right? And okay, somebody does. Well, you search. It's terrible. You know, you have this stupid thing that you can search for. It's a great writer, by the way. He's a really great writer. That's a benefit of knowing Russian. I told you should learn Russian or something else, but I think Russian. I can argue why. Absolutely. You know, I can give you an absolute reason why Russian is the language to learn. So, okay, guys, you understood the question? The question is, what's the probability this guy, so his first and last name, each of them is either Quilty or Humbert. Yes, so that's the question, right? So the question is, what's the probability his full name is Humbert, given that she is wearing one of 3 pairs of her favorite sunglasses? Go ahead, calculate. Okay, Chabelle says 1/3. Naomi says 1/3. Interesting. Okay, let's see. Alejandro says 1/3. Kazi, I suppose it means also 1/3. Yes. Shotaro 1/3. Kan 1/3. Okay. And you say 1/3 because, and Melissa says 1/3. Interesting, right? Because you say it doesn't matter, right? That the sunglasses don't matter here, yes? Mm-hmm. Mm-hmm. Okay, good, good. So, okay, right, so you were quick with the answer. Ready? Yeah, so let's analyze this. Okay, so what information, what's our sample space? I mean, you might actually argue there are many more things happening here, but it seems that the sample space is like this, right? First name, last name, sunglasses, right? So she can be wearing one of 3 sunglasses, but she chose to wear sunglass number 1. Yes. And the fact that she knows that one of the names is Humbert, the possibilities are Humbert Quilty, Quilty Humbert, or Humbert Humbert, right? So there are 3 equally likely outcomes, and the answer is therefore, as you said, 1/3. Good. You see why? Because we have 3 equally likely outcomes. And you said sunglasses have nothing to do with it. Yes, it doesn't matter that she's looking through her favorite sunglasses, sunglasses number 1. Okay, let's look at the next question. Suppose your neighbor has 2 dogs. Each dog is either white or brown. Each of them has one of 3 favorite dishes. Good? Same dishes for both of them, same selection. What is the probability that both dogs are brown if you see a brown dog eating its favorite dish in your neighborhood's yard? Kazi says 1/2. Thank you, Kazi. Okay. Abhishek says 1/2. Thank you, Abhishek. Shotaro says 1/4. Thank you, Shotaro. Interesting, right? We don't know, right? So let's say, so you understand the way I thought of the problem. There are 3 dishes that are given to both of those dogs, and each of them has his favorite dish. Could be the same, could be not. Good? You understand? There are just 3 dishes to speak of. Yes, Kazi, we can speak after class, no trouble, right? So no problem. Okay, Shotaro, you think it's still 1/2. I like, yes, I'm enjoying it. Naomi says 1/3. Thank you, Naomi. I think I've seen the movie 21. There was a real guy that it's based on. Sandy says 1/2. Who else said anything here? Okay. What about you, Alejandro? Wonder what you would say. Okay, interesting. All right, guys, let's talk about it. So the answer is not 1/2. The answer is not 1/3. I caught you, right? Although it's a little, yes, Alejandro, right? I was hoping I will catch all of you, but maybe some of you remember. I already asked this question or a version of it before, and we talked about it. Okay, so here is let's say the three foods. Let's say 1 is iams, 2 is kibbles and bits, 3 is pedigree. Okay, and let B be the outcome that the dog is brown, W be the outcome that the dog is white. Okay, so first question, I mean, again, of course, you might think maybe brown dogs are more common than white dogs. Let's assume that none of it exists for this problem. Let's say brown dogs are just as common as white dogs. You have not just no preference. Let's say there is objectively, it's really about flipping coins. It's really something that's what we are modeling to explain the idea. Does having a favorite food imply something about color of fur? No, it does not, right? Just like in the previous problem, you would say the glasses that you are wearing don't imply whether your name is Humberto, yes? But you are making a crucial mistake in your reasoning. Let me explain what that mistake is, okay? What are you counting? When you do probability, you are counting the universe. You're not counting the brown dog, and it's not cause and effect, you understand? You are making the mistake of selecting the wrong object. In fact, that's what I mentioned about Hans Dürer. If you read my email today, is that you see, when you think of probability, you think of the universe as one entire thing, as one thing. There is no difference. Those are just features of the universe that you're observing. Okay, so here is look at it, guys. Here is my Kafka document, right? So the Kafka document for the full sample space is old dog, brown or white. Choice of food for the old dog. Then young dog, brown or white. Choice of food, okay? So the full sample space has 2 times 3 possibilities, or 6 times 6 possibilities, 36 possibilities in total. But what we have observed, and all of them, let's say, are equally likely. We're presuming all of them are equally likely. That's not true necessarily in life, but that's what what we're thinking here. So what are we observing, guys? Are you with me? We are either observing the old dog, which likes food number 1, or we are observing the young dog, which likes food number 1. Okay? We are observing a universe or part of it that looks like this, or part of it that looks like this. You understand? But the thing that we're observing is one whole universe. It contains both dogs, both their colors, and the food. Now, how many possible outcomes in this in those universes? So this universe, look at it here. This universe that begins with B1 has 2 times 3 possibilities, 6 possibilities. Yes, this has 6 possibilities. This other universe also has 6 possibilities, and just as Alejandro noticed, we are overcounting one possibility because both of those universe types contain one universe in common, namely B1, B1. Do you see that? B1, B1 is the universe that will be contained in common. So that's why I subtract 1, because here I counted it once, here I counted it again once, I counted it twice, so I subtract 1. Right? So I have 11 possible universes to observe. How many of those universes correspond to both dogs being brown? That's the type of universe that I observe where both dogs are brown, or that's the type of universe where I observe that both dogs are brown and one of them likes keep whatever is number 1, right? Iams or something, right? You see that? Are you with me, guys? So how many possibilities? Just like it before, there are 3 possibilities here, 3 possibilities here, but 1 counted too many times. So it's 3 plus 3 minus 1, or 5 possibilities. The probability is 5 divided by 11. Are you with me? Would you give me another 5 minutes to finish this full lecture? If you can't, you can go. I will just like to finish this one point. Okay, what's your mistake? When you ignored the glasses, you said, well, glasses don't affect the name. You are basically not looking at the universe as a whole. Okay, glasses do narrow down the universe in which you're living. Every information, in fact, if you say the window through which the guy is staring at Dolores is narrowing down the universes that are possible. Are you with me? So what you're always counting in probability is you have a sample space, and within the sample space you have possible universes, including everything in them. And when you are looking at a particular feature, like both dogs are brown, you're searching for those universes in which this feature is present, that both dogs are brown, but you are still counting those universes. Do you understand? You can so here is an example of that, for example, right? So some information, why do you ignore it, and other information you don't ignore. Here is why. So when you calculate the probability of E without any extra information, you just count how many universes contain the property E divided by total number of universes. And here I'm assuming each universe is equally likely when I say this ratio. It's actually more complicated than that, yes? But if they're equally likely, that's just the ratio of possible universes with feature E divided by total universes, yes? Yeah, so sometimes this ratio, you see, whenever you get, whenever you give some information about the universe, you restrict possibly the total number, because now it's more definite. There are fewer possibilities. Every time you say something, every time you present information, you limit possibilities. It becomes from potential, it becomes more of an actual universe, right? The more you say, if you could say everything, it will be just one universe, because you described it, right? As you are describing, you are limiting possibilities. You're with me, right? And you're also limiting the possibilities for the numerator. Good. So here is a simple example, right? Why can sometimes you ignore that information? Because the ratio of those limited possibilities stays the same, but the actual number in the numerator and denominator changed. Here is a very simple example, right? So if two fair dice are rolled, what is the probability that first die is a 6 without any restriction, right? And B, the first die is a 6 given that the sum is equal to 7. Okay, so how do you solve this particular question? So first, in A you have two possibilities. So you have altogether 6 times 6 possibilities, right? And 6y, where y is 6 possibilities, is the number of universes, right? So you have 6 over 36, 6 universes with the desired outcome, with the feature that first die is 6, over 36 possibilities. So 6 over 36. Good? Don't simplify it for a moment. Just keep it as 6 over 36. What happens if I do problem B? The summation is 7. That means that my sample space is restricted to one of 6 outcomes, and only one universe has this feature. Look at it, 1 over 6. Do you see what happened? The numerator universes, the universes that could have this feature, has been limited, but so has been the denominator. So 6 over 36 and 1 over 6. Those are the same number because the ratio is the same, but they express entirely different situation. You see, this one expresses the situation where the potential is limited. Here it's less limited. Okay, and some people, here is what you do. Some people, what you do is, oh, the second die doesn't matter, so I can cross this information, I can just consider X. And this is not correct reasoning, because X is not counting those universes. You understand? What is the correct reasoning? What truly happens and why you don't make mistake when you eliminate the second die from your consideration? I'm asking, what's the probability first die lands on a 6? When you limit the second, when you ignore the second die, you are actually making a logical fallacy, because you're switching your observation from the possible universes to an entirely different class of universes. What I do is this: I actually assume that that I have more information, and I know that second die came out to be 1, and then I can, because the second die came to be 1, I kind of say that I can suppress this information. I don't have to feature it. Okay. And the reason this is justified will be explained in later sections. So you see, it's very, very complicated. But why, when I throw 2 dice, do I consider only the universe is containing only the two dice. It's because I hold everything else to be constant. I imagine I have exact information about everything else, and I just don't want to mention it. That's what I imagine. You understand? It's in some problems it will not matter. You'll get away with doing this, but in some it does matter, because you see, here is what your mistake was. You are asking for cause and effect relationship between X and Y, but you should ask, how is this information limiting the number of universes? Every information limits the number of universes. So every information is important. The fact that Dolores is wearing black glasses limits the universe, the possible universes in which it can exist. The fact that he looks through a window matters. It's because you have his name is Humbert, and the window is, I don't know, 17 by 17, I don't know, or 1 meter by 1 meter. You understand? That limits the universe because that makes it more definite. Maybe it doesn't have the effect on probability, but it does have an effect on the universes. Good, guys? You follow the explanation, I hope? Shotaro left the building. Yes. Good, isn't it interesting, guys? And that's why, I mean, I listened to that what's his name, Hans Dürer. You know, when he's of course he's a quantum physicist, and quantum physics is based on probability. And when you study probability too long, you have this feeling that pretty much you don't exist, the other thing doesn't exist. All that exists are just universes with possibilities, and those are just observed features of those universes. Good, okay. Thank you for staying. If you want to continue to office hours, remain with me. Otherwise, goodbye. Take care, guys. See you very soon.